Math 2414, Differential Equations, Video 2, Separable Differential Equations. As I mentioned in the previous video, the realm of differential equations is a whole other course in its own right. In fact, it's a series of courses. And so we can only tackle just a little bit of the beginning by looking at one particular type of differential equation. And in this case, that type of differential equation is called a separable differential equation. A differential equation is separable if it can be written in the form dy dx equals f of x times g of y. Let's put a box around that. In other words, it's separable if its first derivative is the product of a function of x and a function of y. And as you'll see in a moment, there's a reason why it's called separable. We're going to separate something. We're going to solve this example, dy dx equals x squared over y squared. But before we do, I want to verify that this satisfies the criteria for being separable. To be separable, we simply have to have the first derivative as the product of a function of x and function of y. And although at first glance this is a quotient or a ratio of a function of x and function of y, we could, if we were pressed to do so, write this as x squared times 1 over y squared. So really, when you see product, you can also think quotient, since a quotient is just a product involving a reciprocal. So it is a separable differential equation, and it's not necessary to literally manipulate it into the product of a function of x and a function of y, although you're welcome to do so. So how do we solve one of these things? Well, the way we solve this lies in the name of the type of equation, separable. The goal is to separate x's and y's. And when I say separate, I mean put all of the y's on one side, all of the x's on the other. Now this includes the differentials, the dy and the dx. Even though this dy dx is technically not a fraction, it's just a notation, we can treat it like a fraction and get away with it, in the sense that if we want to eliminate the fraction, we can multiply both sides by its denominator. So if we're going to separate this, let's think about what we would need to do to get all the x's on one side and all the y's on the other. Let's start with the differentials, the dy and the dx. Since the dy is in the excuse me, a little dry throat there. Let me drink water real quick. But since the dy is in the numerator, we want to kind of leave it there because we really don't want our differentials in denominators. So we're going to start separating this by multiplying both sides of this equation by dx. On the left, the dx's cancel, if you will. And that leaves us dy is equal to x squared over y squared dx. So we've successfully separated all the x's on the right side, the x squared and the dx. However, the y's aren't separated from the x's because we still have a y squared on the right side, but we can fix that by multiplying both sides by y squared. And that will give us y squared dy is equal to x squared dx. Now, I'll admit we could have gotten there a lot faster. You could look at this and say, well, if I cross multiply, that will work, or if I multiply both sides by y squared and dx, that will work. But this is why it's called a separable differential equation. We successfully separated all of the y factors on the left and all of the x factors on the right. Recall that a factor is part of the multiplication problem. All right, so we've separated, but we haven't solved it yet, because to solve it means to find out what y equals as a function of x. So now what do we do? Well, once you've separated, then you just integrate. We should probably document the steps that we're doing, and I'll document them over here. Number 1, separate x's and y's, meaning all x's on one side, all y's on the other. Number 2, integrate both sides. And don't forget to use plus c. So let's move this up and integrate it. Let's see, we're going to integrate y squared dy on the left and integrate x squared dx. Both of these are really trivial. I'm not going to lie to you, in some of the questions in the homework I'm going to assign, the issue is going to be actually doing the integration, not the physical separation. But both of these are easy. The integral of y squared is 1/3 y cubed. And we can put a plus c there. And the integral of the x squared dx is 1/3 x cubed. And we can do another plus c over here. But the problem is I just wrote the same constant twice, and those never guarantee that they're going to be the same constants. So I could subscript them with 1 and 2 or x and y or something to make them look different. Or even use different letters like c and d. But even that's a little bit redundant. The reason it's redundant is we have some unknown constant on the left and also another unknown constant on the right. If I were to move the unknown constant on the left over to the right by subtracting it, then on the right side we would have the difference of these two constants. But guess what the difference of two constants is? Just another constant. So it's really not necessary to put the constants on both sides, because if we did, we can move one to the other side, merge it with the other constant, and just give it a new name. So over here where I said use plus c, I'm going to take off a period and put on one side only. On one side only. And again, that's because we can always move them to the same side and merge them into some other constant that we don't happen to know. Now, is this the solution to the differential equation? Well, you could argue that it is, because if we took the derivative implicitly across here and solve for dy dx, it would satisfy that equation. But when you're solving a differential equation, your goal is to actually come up with a function y equals f of x. So if possible, solve for y. To find your function. And this one's not that hard to solve for. All we have to do is get y by itself. We can start by multiplying both sides by 3. And let's see what that does. In practice, I would think multiply by 3 and then just write the results. The 3 would cancel the 1/3 on the left, leaving a y to the 3rd power. The 3 would distribute on the right. When it multiplies by the 1/3 x cubed, it cancels the 1/3, leaving x to the 3rd power. And guess what 3 times c is? Now, if you said 3c, you're not wrong, but remember, that c just represents an unknown constant. So if you have an unknown constant and you multiply it by 3, it just becomes a different constant. Constant arithmetic is kind of funny because you usually just keep writing the same thing. 3 times a constant is a constant. Now, there are some authors, professors, and textbooks that will say, no, you can't do that. You have to put something to say it's a different constant, like a prime or a subscript or something. But as long as we're just saying there's a constant over there, it really doesn't matter what it's called. So 3 times a constant is just another constant. But we're not done yet. We haven't solved for y yet. We can do that by simply taking the cube root of both sides. This time I'll just say the move, cube root of both sides, and then execute it. Now, I know what some of you are thinking. Can't I cancel the cube root with the cube on the x? And the answer is no, you can't. Why? Because of this plus sign. You cannot distribute a power or a radical across a plus or a minus. If I could, this would become an x, this would become a different constant, but unfortunately, you cannot distribute a radical across a plus sign. So that would be the end of it. And if we wanted to check this, we would have to take the derivative and show that it satisfies this. Well, let's check it. We have a tentative solution. Let's write it here. Y equals the cube root of x cubed plus c. And just for kicks and giggles, we're going to check it. All we need is the first derivative. So we might want to write this as a 1/3 squared power, because we don't do calculus to radicals, we do calculus to exponents. And so the derivative, which we'll go ahead and call dy dx, is equal to 1/3, parentheses, x cubed plus the constant that we don't know, to the negative 2/3 power, subtract 1 from the exponent. Chain rule says times the derivative of the inside. The derivative of the inside is 3x squared. And let's clean this up a little bit. The 3's cancel, the 3 and the 1/3 I should say. And if we write this as a fraction, because we have a negative exponent, the x squared would go on top, and we would have x cubed plus c to the 2/3 on the bottom. Now, do I want to turn that back into a radical? Well, I don't know if I want to do that, but I do want to see if this is equal to that. So let's set up x squared over y squared and see what happens. Well, if we set up x squared over y squared, we want the x squared, so that's good. But let's replace the y with what it equals. The y is equal to x cubed plus c to the 1/3, but that y is getting squared. We have an exponent raised to an exponent, and so we multiply them. 1/3 times 2 is 2/3, and if you notice, these match. So it is a solution to the differential equation. It's what would be called a general solution, because any function that looks like this, meaning I can put any number here I want, will be a solution. If we put a number in there, for example, if we put in c equals 1 or c equals negative 12 or c equals 0, we would get what's called a particular solution. With the c, it's called a general solution.